and we made it work. And actually,
Okay, we've still been waiting for David, but he's going to disappear after his keynote. So, my name is Jarek Nawczyński. I'm representing the University of Notre here and also the DASPOS project. And welcome to the joint workshop between DASPOS and I have to be careful, digital preservation of research methods and artifacts. That is actually led by David. So my background is computer science, but with the DASPOS project, we're coming primarily, hydrogen physics, and hydrogen physicists are our major, I would say, contributors or users. We all know the problems that they face with the amount of data they generate and analysis needs, etc. And the question, of course, is what we're going to do, how we're going to preserve this data for the future times when we want to go back and use new research methods on the same data. I won't be going into details. I think we have a very nice program that we can cover these details during what which. But my idea was really to go around the table and see, introduce ourselves, see who is in a role, so we have a better view, what's going to happen next. So I would recommend that maybe Regan, you're going to start.
Hello, I'm Regan Moore, University of North Carolina at Chapel Hill, and I work on policy-based data management.
Hi, I'm Ben Campagne. I work at Data Archiving and Network Services in the Netherlands, and I'm here for the DPRMA workshop.
Hi, I'm George Strawn. I run a small Washington office called Networking and Information Technology Research and Development, which purports to coordinate the IT research programs of 20 federal agencies.
I'm Beth Playley. I'm a faculty member in the School of Informatics and Computing at Indiana University, and I'm also on the Seed DataNet project and also research data lines. And a big fan of research projects and preservation.
My name is Douglas Thain. I'm at the University of Notre Dame. My specialty is in large-scale distributed computing, and that occasionally collides with hydrogen physics.
My name is Gordon Watts. I'm at the University of Washington. I am a hydrogen physicist who is part of this DASPOS collaboration.
Elizabeth Long, I'm an Associate University Librarian for Digital Services at the University of Chicago, and I'm also part of the DASPOS project.
Brad Hemming, I'm at the University of North Carolina, Chapel Hill, going for Regan, School of Information Library Science, the mainly scholar communications, but I'm a fan of flipping anything, in particular interested is really data collection. That's managed.
Lynn Bouchard, I'm a staff scientist at Oak Ridge National Lab in the Scientific Data Group, and I'm part of the Data One project, which has a cyber infrastructure at DASPOS people are contributing.
I'm Raúl Palma. I am working in personal supercomputing and networking sector in Poland. I'm working in aspects related to semantic web technologies, intelligent engineering, and in digital preservation. And in particular, I'm working also in a project called Motor that also seems to be by David.
Hey, I'm Margaret Jan. I just graduated from Indiana University with my MLS, and I'm interested in open science.
Rob Sanderson from SLMOS National Laboratory. I work on the Memento project, which is about access to historical versions of group registers and scientific and scholarly research projects.
Hi, I'm Michael Altman. I'm a social scientist and an information scientist, the director of research at MIT Libraries. I'm a resident senior fellow at Brookings. Been involved in preservation for a while on the coordinating committee from the National Stewardship Alliance, steering committee for Data Pass, blah, 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 blah. And lots of projects, blah, blah, blah.
Hi, I'm Cezary Mazurek. I'm from Poznań Supercomputing and Networking Center in Poland. I'm leading the Department of Network Services, but most important here is that I'm leading several programs several programs at TSMC, and one of the programs is building the infrastructure for digital libraries. This infrastructure is also used for storing the research objects in workflow for other programs. And that hat here.
Gary McDonough from the Graduate School of Library and Information Science at the University of Illinois. I've been working for the past few years as the PI on the Preserving Virtual Worlds project, looking at preserving computer games. And I'm also currently working with Carnegie Mellon on the Olive software archive system.
Nick Koo from Drexel University. I guess I'm a qualitative social scientist / ethnographer, and I'm interested in studying the organizational factors which affect how people create and share metadata and how they support interoperability.
Matt Meredith from the National Center for Atmospheric Research, University Corporation for Atmospheric Research, where I'm research data services specialist in the INCAR library. So I'm leading the development of data services out of the INCAR library, as we hear in a little bit, also which also involves working with data management groups around the organization.
My name is Michelle Daniel. I'm with OCLC Research, and my interests are data reuse. So I'm interested in data reuse, particularly contextual information that's important to be able to make that happen and improve history.
Hi, I'm Michael Litt from Purdue University, where I'm a librarian and the director of our institutional data repository service, which is called PERC. And the focus lately has been on trying to translate theory, rhetoric, data curation, issues, and data needs assessments to practices and tools that the libraries and librarians can implement.
Hi, I'm Chris Matman. I kind of wear 3 hats. I'm at the National Aeronautics and Space Administration. I build and have teams that build remote sensing systems of the Earth and systems for planetary data system archiving. I'm an adjunct assistant professor of computer science at USC, and I'm a member of the board of directors of the Apache Software Foundation. So I help create tools like Nutch, Hadoop, Lucene, Zika, Solar, and other things that are used in digital libraries. So, thanks for having me.
Hi, I'm Rob Gardner from the University of Chicago. I work on very large-scale data-intensive computing for high-energy physics, and I'm part of the DASPOS project.
I'm Don Petrovic. I'm from the National Center for Supercomputing Applications at the University of Illinois. I'm the principal investigator for the Dark Energy Survey Data Management System, which is the system that reduces and produces catalogs for the Dark Energy Science Collaboration.
Thank you.
I'm Charles Vardaman. I am a computational scientist in the Center for Research Computing at Notre Dame, and I'm associated with the DASPOS project.
Hi, I'm Callie O'Connell. I'm from the Center for Research Computing at the University of Notre Dame, and I work on public relations and event coordinating. So I have emails with a lot of you.
Benoît Rebo, Center for Research Computing at the University of Notre Dame as well.
I'm Cliff Lynch. I'm the director of the Coalition for Networked Information. We have a range of interests in research and management.
Thank you. Welcome, David.
Hi, I think, does everyone know me?
I think so. Nancy, did you have a chance to introduce yourself?
I'm a e-research and digital librarian at University of Notre Dame.
Okay. David, why don't you join me here? Sure. So yeah, about the workshop, I wanted maybe to say a few words why this workshop and what we are interested as a DASPOS project in. So in our NSF proposal, the project is funded by NSF. We promised to organize 9 workshops in 3 each year, basically, in which we're gonna define our scenarios, use cases, but also connect to other communities like today and find out about common commonalities or commonalities between the projects and different sciences. So this is what we'd like to get out from this project today. I assume and I understand your, David, goals are very similar. Yeah, just to kick off the workshop, I think we're going to have 2 panels at the very beginning, at the very first session, and then we're going to have presentations from our colleagues' workshop, right? So they will be running this one. And then we're going to have some more breakout sessions where we're going to break up for panel roundtable discussions, and then we will convene and have some kind of cool discussions on discussions. I won't be going through my slides because we are already kind of late. Yeah, who's running the first workshop? Yes, Laura. So the stage is yours.
Okay. All right, thanks. So for this first roundtable, we've got 4 people. I assume you guys can hear without a microphone. Chris Mutman, Reagan Moore, Don Petrovic, and George Strong. We'll go in that order. It's set up for everybody to do 10 minutes of either a talk or a demo, and after that, there'll be about 15 minutes for discussion. So, are you running? So, Chris is first.
Yeah.
And I'll yell at you around 9 minutes.
Cool. Let's see if I can finish in 7. All right. So, hey, I'm Chris Nevin. So, I was thinking about this, like what I would talk about. I wanted to talk to you guys about something related to open source, because I think it's an important part of understanding sustainability, at least for software. So I'm going to tell you how we develop open source software at NASA, or how I learned to stuff. So you know who I am. I told you I was. So forget about that. So I work on a lot of projects. You guys work on a lot of projects. I heard when we were around the table the kind of diversity, at least in the types of projects we work on. 2 ones that are really important to me that I think just set the context. One is the U.S. National Climate Assessment. The project that I'm working on there is, 2 of them. One of them is to build a snow and ice climatology for the western U.S. and Alaska. And that project involves the use of open source software. We're putting together sort of these big data, whatever you want to call them, digital library type of technologies for archiving upstream MODIS hyperspectral data, and then we convert it. As it turns out, the standard NASA snow data product for surface reflectance is binary. It's snow or no snow. So you have a 50% chance of either overestimating the snow or underestimating it. And that pretty much screws water managers when they try to figure out how much water to release from dams or to hold in there and stuff. So we're trying to alleviate that through a number of projects in the National Climate Assessment. Another interesting one, I heard someone or a couple people mention sort of dark energy physics and astronomy. The square kilometer array is the next generation instrument for that. After a long discussion between South Africa and Australia, they decided to sort of build it in both locations. It's going to generate large amounts of data, and because of astronomy moving into the time domain, and the old adage of the skywing archive kind of going away in that context, we need to store some of the data and keep it around, and so it's turning into sort of a big data problem. And open source is helping there a lot because, as it turns out, we don't have a ton of support for dealing with the SK specifically yet in the US, and so one way that we've gotten around it has been to share software, for instance, with the South Africans working on the SK South Africa project through open source, through the Apache Software Foundation. So, most people, when they think about software development, they think about the green field, right? And they don't necessarily think about standing on the shoulders of others, like Dr. Ian Malcolm told us in Jurassic Park, right? And the fact that they do it. They don't realize that they're actually standing on the shoulders of others when you take software and you reuse it, or when you take open source software or these data systems and put it together into sort of a collective work. In fact, how many people here know what a collective work is? With respect to software licensing, or the difference between that and a derivative work? Okay, all right, well that's important, right? Because we need to know that. So hopefully we can talk about that during the discussion session, because it's important. What I'm interested in doing is more generating the hive, right? To generate something bigger. Is to put people together who are building software communities and to connect those communities together, and then to realize the sort of differences between them when we're building, these digital libraries, these data management, these archiving systems, or whatever the application. Bioinformatics, earth science, remote sensing, things like that. So at NASA, all the bad, mean policy people come out and say, well, your government agency can't do this. There's this thing called the FAR supplement that governs the way that you guys share software with one another. I can't share software with Ames. supercomputing with them, or I didn't say that, I work at JPL, or Goddard, or things like that, right? So, you know, and then there's all these other system engineering policies that dictate, you know, the risk and the use of software components and data management and things like that. There's also your center's interests, you know, but what about, you know, what my project manager told me as a developer, you know, there's this aversion to using that type of software and open source and things like that. It's risky, it's, you know, more difficult to leverage. What about what the guy in the next cube told me about, you know, his new cool technology that saved him time? And then they would say, like, well, what about the stop thing? What about, you know, you think that's there, you're breathing out there, you know, you're living in the matrix, right? You know, besides that, a lot of the misunderstanding, or not misunderstanding, but just the lack of, I'd say, due diligence when it comes to understanding how you leverage software components when you build data management systems comes to the fact that most people at an agency, and I'm not just talking the government, say at a university, how many of you guys can draw your open source process? Yeah. How many of you guys can draw the way that you consume open source software, or even the way that you produce it? Right? So it typically boils down to that. It boils down to that from a preservation perspective too, right? Because if you don't know how you're consuming sort of software when you put it together into a product, you don't know how to save it, right? And if you don't know how to produce it, or what the, you know, the processes that did that, you know, it's more difficult to understand what people were thinking when they did that. This is a very simplified version of the NASA process. If you read the diagram from left to right, you know, this is the production-oriented part of that process. So you wrote some cool software. Here's what you have to do. NASA uses a process called the New Technology Reporting Process to basically uncover trademarks and commercialization and export and ITAR and other concerns that we have for releasing our software. They trick us, they don't trick us, but they incentivize us as software developers there to basically describe what we did in the new innovation, and that kicks off behind the scenes in our software center release authorities these investigations into that. And our reward for writing those NTRs is a small monetary amount. It gives a couple $100 basically, and they give us a little award and a plaque. You know, it says we did a good job for that. And what's going on in the background is that they're deciding, is this ground software, is this flight software, you know, and based on those types of classifications, you know, whether or not we're going to be able to actually, and then it goes up to headquarters, and then they decide, and then they come back and they decide whether or not, you know, you can actually take it. If there's no commercialization interest, if there's no export control in ITAR, you're in business. Take the software and you can put it into open source. So the duration of each arrow and step and size of those bubbles can vary, and that's what makes people think they can't do this. Because it took 2 years for one guy, 6 months for another guy, and, you know, they didn't understand why. Open source is really important. I think a number of the projects, you know, and people here, you use open source software, you may produce it, which is really interesting. You find that less often, and you find lots of people putting together these open source products, but not necessarily going and pushing up into the communities and producing them. That's good too. We need to do both. And we need to do it in a way where no one organization controls the software. That's another real key thing for sustainability, in my opinion. One organization controls, if Oracle is releasing Oracle 11 to you, and they give you the source code, they call that open source, don't believe them, it's not. Because you'll never influence what Oracle is doing in terms of what, you know, they're going to do when they're releasing their software. You'll influence them by reporting bugs and everything, but they're the ones that control and stewards the software. And I'm a bigger fan, and I think we need to move in open science and things towards organizations that are based on meritocracy. The contributions that you make to those projects ought to earn you the commitment and the merit to steward and govern those projects, right? And not all foundations and organizations are set up that way. Apache Software Foundation, sorry it is, that's the way it's set up. Basically, you earn merit. You can earn merit at the project level, which are these decentralized communities of building interesting and diverse software projects. As you earn merit, you gain more responsibility in the project. Initially, you're submitting patches. Eventually, after that, you become a committer. You can decide and vote on the addition of new people to your project and on the release of the software, which are the two formal decisions that projects make at Apache. Eventually, you can become a chair of a project management committee, an officer of the foundation, a director, a member, things like that, and that's all going up the merit hierarchy. And then, additionally, there's a process for bringing new projects in. There's an incubation process. There's a process for, you know, graduating, you know, projects and getting them out there. Worried about the loss of control? Don't. As it turns out, this is loose consensus, not unilateral agreement. That happens to work in these sort of diverse communities of building software. It's community over code. What that loss of control has bought my team, my projects, and I is basically, if you write a grant with me or we do a grant with you guys across any one of the number of projects I do, you can hit the ground running day one, and you can start sharing the software and you can start contributing to it most of the time, because most organizations, most academic government organizations, have the ability to contribute to permissive licensed projects, and they also have the ability to contribute to these types of efforts. So thereby generating more diverse organizational interest and ultimately more sustainability and diversity, and of course RESPCT. So besides that, I hear a lot of that. So all this doing work for my mission, open source, whatever, we got to build it. We got to build the database from scratch. As it turns out, it's worked for a lot of them, and a lot of the recent ones that are about to fly. OCO2, OCO1, the NPOS preparatory project, which is the next generation polar orbiting satellites, and the SNAP, Inner Science Soil Moisture, is about to fly. Here's an example of a project that really got into this. Apache ODT is for NASA's first project. We were able to bring to the Apache Software Foundation. We brought it there, and effectively what it is, it's a data management technology, really exemplar example of this. The really interesting thing is it didn't start in open source. We brought it from government there. What ODT lets us do is handle a number of these big data challenges. I'm going to skip that because I'm low on time. Basically, what I wanted to kind of just highlight is, and I'll kind of end here, is that this is what we're up against a lot of times with government and academia and industries. We're competing against, these companies that have bags of money to hand talent that's coming out of universities. I see it all the time. And most of the time, the only thing we really can compete with, if we think about it, a lot of times is the game-changing challenges that we have at our organizations. Luring students away from Facebook because they don't care about figuring out who poked who, but they might care about high energy physics or, remote sensing of the Earth or saving water for people and things like that. So open source is an enabler to that because it allows us to field test them at the academic level on projects before we get them in our institutions and universities, get the right people there. They get reciprocal benefit, they get merit, as long as they participate in these permissive areas like that. We want to enable that next generation of super engineers. I'm going to skip that, skip that, skip that, skip that, skip that, and then here. There you go. That's me, Chris Mann on Twitter.
Thanks, Chris. What I'd like is if people have particular questions to hold on to them so that perhaps we can use them to generate discussion once all of the 10-minute talks are done. So next is Rick Moore.
This is the right one.
Yep. It's got your name.
I'm going to switch gears and talk about the future. At the University of North Carolina, Chapel Hill and the DICE group, we've been very interested in trying to understand what are the generic properties of data management systems such that you can build an environment that's capable of managing all these different applications on the same generic infrastructure. So the approach we've taken is to try to understand what are the correct virtualization mechanisms so I can do this in a distributed environment. What does it mean to manage data? Do I also have to manage information and knowledge? How would I apply this technology not only for sharing data, but publishing, preserving, analyzing, building processing pipelines? So these are existing projects that are managing petabytes of data in distributed applications that cross administrative domains, and they're doing this around the world. The technology we're using is the Integrated Rule-Oriented Data System, or IRODS. This is software that's built as middleware. It's software you install at each location where you're going to manage data. The server you put at that remote location, or the software, maps from the protocol required by your favorite client to the protocol required by your storage environment. It has a metadata catalog in which it's managing state information. It has a scheduling system, so you can do periodic and deferred execution of policies, run processes within this environment. And it has a messaging system for out-of-band communication, so you can do debugging, you can track progress of individual status of procedures, etc. So within this distributed data management environment, you're managing all of the capabilities normally provided by an operating system. You're managing data, you're managing state information, you're doing communication, you're doing execution, you're executing procedures. When we look at that environment, we had to come up with how we were going to control what was happening in the distributed world. So from the perspective of a data management application, there's some driving purpose for why we want to build a collection. Based upon that purpose, there are a set of properties we want the collection to have. To enforce those properties, we create policies. The policies control the execution of procedures, which actually do the required operations within the distributed environment. The execution of a procedure generates state information that we then have to manage. So a standard policy might be integrity, which I'm going to implement by replication. I need a procedure to actually replicate the data, and I have to store somewhere the location of the replica. I can then verify whether or not the system is working accurately by running periodic policies that allow me to go in and check that a given property has been conserved over time. If we look at preservation, we recognize that we really needed to manage not just the records or the data, we also had to manage information and knowledge. From the perspective of preservation as communication with the future, we have to provide a context such that somebody in the future can understand why we bothered to preserve this particular record. That's typically managed as information attributes associated with the record itself. But preservation is also communication from the past, and I have to be able to verify an assertion that prior archivists have made about the procedures they ran to curate and actually preserve the record itself. So we think of knowledge then as the procedures, workflows, analysis systems in which we've encapsulated the policies that the archivist wants to conserve over time. And therefore, when we build a preservation environment, we have to manage the data, we have to provide information about the data, we have to provide knowledge procedures that allow us to verify that everything is worked correctly. When we talk about capturing knowledge, we then, from the perspective of reproducible data-driven science, have three types of knowledge we need to capture. We need to think about the knowledge required to acquire the data. How do I interact with the remote resource and bring that data into my environment? I have to use their protocol to do it. Capturing that knowledge of that protocol is a form of knowledge encapsulation. I then have to capture the knowledge associated with the procedures or analyses I'm actually running on the records. How do I transform the records into an archival information package? What procedure was run to do that? Given that I can generate the package that I'm going to preserve, I then need the knowledge about how I'm going to manage the records themselves. What are the policies under which I'm going to enforce chain of custody, authenticity, etc. So we had to have knowledge related to ingestion, knowledge related to the analysis, and then knowledge related to the management of the product. A nice example we worked with in the hydrology domain is automating the acquisition of data required to do a hydrology watershed analysis. Their challenge is they have to acquire data from many different federal agencies. They have to get digital elevation maps from USGS. They've got to get soils data from Department of Agriculture. They've got to get leaf index from, in this case, analysis of data sets that NASA has. We've got to get infrastructure from the Department of Transportation. Each of those resources uses a different protocol, and therefore they want to be able to capture in a basic function the knowledge of how to interact with that remote repository so they can automate that interaction in the future. They then compose all these steps into a workflow, and they want to manage that workflow within the same environment in which they're managing the products from analyzing the watershed. To do that, we now are registering workflows as entities within the data management environment. So given a workflow, I can then associate automatically a collection with it. I can put my input files in that collection. When I run and execute an input file, I automatically create an output collection, and I can store my output products. So the process of running the analysis is now automated, including the capture of provenance information. So I can share the input, I can share the workflow, I can share the output. I can change the input, rerun, and compare output results. I can do reproducible data-driven research. So this is one large concept graph which tells you how we organized or implemented a prior chart I showed you, where we went from the purpose to the properties to the policies to the procedures. In practice, when we define a purpose, then we have to pick what properties we're going to apply. If we pick an integrity property, I then have to implement a policy that enforces integrity. which might mean a policy related to replication, a policy related to checksumming. I then need a procedure that will be executed to actually do the replication, create the checksum, and verify it. I then have to store that persistent state information somewhere so in the future I can look and see what was done. If you go down to the bottom where there's a client, the client will invoke an action in this environment. It's trapped by a policy enforcement point, which automatically applies the correct procedure then to enforce integrity. So this gives you an end-to-end environment in which you can implement the policies you require, manage your state information, manage the knowledge required to run the procedures that do your type of processing. So the technology we're using to do this is iRods. It's open source software. There's a community of roughly 10 contributors around the world supporting this, and it's been funded through the National Science Foundation and the National Archives. Thank you.
Okay, Don?
So this is a talk about the Dark Energy Survey Data Management System and the Dark Energy Science Collaboration that stands there. This is just to orient you. This is a picture we took data on a rather large camera in Chile, an iconic picture. I have to show it. These are the goals of the dark energy. These are parameters and the objects that will be measured. And basically, the idea is to study the expansion of the universe, which everybody understands is now accelerating, not slowing down. And the Dark Energy Survey is designed to extract these parameters and allow the study of dark energy. We don't do that at NCSA, the Dark Energy Data Management System. We produce the data sets that allow this analysis. We tend to think of astronomy as pretty pictures, and we saw earlier talks today about Worldwide Telescope and such. I think practical professional cosmology is a little different. Our camera is, what I've shown here is does that show through? Yes, okay. Our camera is a mosaic of 62 CCDs. You can see they've put together, there's small gaps in them. And what we do is we image the sky, we shift a little bit, image the sky again, shift a little bit, image the sky again, come back at some optimal time later, image it again to report systematic effects in the atmosphere and whatnot. And what we do is we kind of build a picture. And the picture, of course, because of the seams and the shifting, is not of uniform depth. And so when one studies the images or any of the data that comes from the images, there's all this sampling bias in it. Right? So if you look here, I think you can see that when we put things together, there's all this fine structure that goes with it. So we make images, they're not ideal. They're accumulated to get maximum signal to noise. Maximum signal to noise varies almost at the pixel to pixel scale. Right? This allows the study of things like clustered weak lensing. And the point where I'm going for is while we get images and we go quite deeply, it isn't classical image analysis like you might imagine somebody scanning a photo for features. What we actually do is build catalogs, and we parameterize the objects, and we build about 250 parameters for every what we call single epoch image, and altogether the scientists have about 1,000 parameters because we image the sky in 5 filters, and so you get kind of a crude spectra out of this thing. So the nature of the whole effort is it's kind of a decade duration. We had a year of science verification. We will take data for 5 years. We'll spend 1 more year producing a final data release, and the preliminary building of the instrument and all the software was 4 to 6 years at a time. So the thing is order kind of $100 million. It's not Atlas, it's not CMS, it's not LHCb, but it's not non-trivial, right? The survey products are broadly reusable, but the focus we have is on study of dark energy. A bit unlike the Sloan. The Sloan, I think, was more science agnostic, right? And as I said, we are a bit like high energy physics in the sense that what we really support is scientists doing statistical analysis. We aren't so much looking at the looking at the pictures as the scientists look at the catalogs. And since that's a derived data product, it matters very, very, very much what the systematics are in computing, in extracting the parameters and presenting them in the catalogs. And that way we're kind of like high energy physics, right? Statistical, there's a statistical basis to our study. And it's one experiment running for 5 years. It's not a bunch of principal investigators taking 3 or 4 nice pictures and doing what they want. So it's a big coherent data set, right? And I can't quite read my own slides here. And so the data, there's a lot of work that goes into the processing of the system, right? You need detailed understanding of the instrument, detailed understanding of the atmospheric signatures, so on and so forth in my list, right? So we do this work, we do it as well as we can, we do it up front, and we have about 30 people who think about whether the data are good or bad in our experiment, right? When we process it, these are steps. I'm not quite sure if they're meaningful to you, but basically we take the images, we process them, we remove the instrumental signature, we troll them, we make catalogs. There's about 250 objects, as I said, per detection. We take the images, we all register them on top of each other, and we go deep, right? We build COAD images out of that, we build catalogs out of those again, we build the mangle masks that I showed you. We do supernova detections too as well in our spare time. We do photometric redshifts and we build weak lensing catalogs. Everybody has a picture of a workflow system there. Right. Data volume for us is over the 5 years we'll have 10 million images, and each image is about 8 megapixels, and with an additional 8 megapixels of weights and masks that come with it. It's all astronomy data. It compresses very well. Processed reduced image is 20% the size of the inflated version. We have about 100 we'll have about 100 terabytes of catalogs with billions of object detections, mangle mask, and all the other stuff that you need to interpret the data. We store all the stuff except for the images in a relational database that has a query capability, because the astronomy community is used to querying databases to go get data, and they like kind of spatial queries, like what are the things like this near those things. Right. So that's the kind of capability that people want. We'll also build about 50,000 very deep co-edited images, where the co-edited images are much larger than the exposures. And altogether, it's about 2.5 petabytes of file data. So that's what we do with DECAM images, and we let it go to the we let that out to the collaboration. That is not the sole data set on which the science rests. There's independent efforts in the collaboration outside of what we do at NCSA to produce cosmology simulations, and the basic game is simulate the cosmology, suppose the physics of the universe is like this, build a simulation, build catalogs, and look at it as if we would have observed it with DECAM and compare. That's the utility of the mangle mask, for example, when you sample your simulated cosmology, you want to take signals from noise and do it the same way. So the analysis is, it's kind of sophisticated. Also, astronomy is, people care about data to the astrophysical universe, and of course, we're an instrument with a detector technology, some filters, and can observe the heavens in a certain way. It's all the scientists that may or may not be the best data set for extracting a science goal. And there's always interest in astronomy with combining data from other surveys. So, for example, we have a strong interest in this VISTA survey, which is in the infrared, and we don't have a detector that does infrared. We have an optical detector. Right? Can't do two things at once. Then lastly, on top of the data products we produce, the science working groups and other people would produce what are colloquially called value-added catalogs. They will produce additional derived data products on top of ours, which sometimes are more reused than the fundamental data set. Right. So preservation requirements. What was written when the smart people set up the survey? This is before I came on board. Right. The DES science images that we take are archived at NOAO because we are a prime user and have donated the camera. But basically, this is an NOAO facility instrument, and we get the majority of the time on it, but not all the time. So NOAO holds the raw images. Right? Any calibration images taken on DECAM are immediately available because the people need that sort of stuff, and there's no reason to waste the telescope time picking again. Transient information, we detect supernovas with a 1-day latency. That information is available immediately to the community in the form of an astronomical telegram, which is a colloquial name for some event distribution system. It's got a tiny form of font, right? Our reduced images are available a year after we take it because of the proprietary data right. We make 2 releases of our catalogs and all of our big stuff to the public, and we develop and the requirements tell us to develop documentation at the level of peer-reviewed papers. A full system, I think, would have a technical dimension and a support dimension. The technical dimension would contain very detailed documentation of all the data elements, including calibrations, full provenance. We would retain the instrument and environmental records of observer actions, right? Was the moon up? Was it cloudy? That sort of thing was the instrument that tells us the moon is up, was cloudy, gone bad. Well-documented codes in a reasonable technical basis, a salute to open source where possible, right? That achieves that. Well-documented processes, that what did we do? Inclusion of value added in other catalogs. And then if you have all that and you preserve all that, what do people need to use it, right? Suitable access methods. So right now I have a 128 core Oracle database that people can query against. That's it wasn't that expensive truly, but it's a piece of technology that has to be sustained. For sustained use, that's a problem, right? Suitable support, knowledge about data. It's some sort of solid institution that is not a project that goes away. So my summary is that we have a large investment, 10-year investment, something like $100 million in this thing, lots of acumen, right? But on the other hand, we produce a lot of data, but to get a lot of science out, multi-instrument data is already needed for analysis, right? The underpinning the data are code, calibration, procedurals, instrument, environmental effects, and our current data management plan preserves the data, but only preserves the acumen and underpinning knowledge and the level of replications that describe what we do.
Thanks, Don.
Yes, good afternoon, everyone. I'm impressed with the goals of the DASPOS organization and project, looking across multiple disciplines to look for best practices, commonalities, and so forth. In a certain extent, that's what my organization of the NITRD interagency organization attempts to do, bring agencies together looking for best practices, collaboration opportunities, and various other forms of coordination. I think agencies, like disciplines, spend a lot of time in their own cylinders of excellence, and burning holes in those cylinders can be a good thing. As the NASA speaker mentioned, I will tell you up front that the opinions expressed in this talk are those of mine, not the U.S. government. I do like to shoot off my mouth from time to time. I do not represent anybody myself when I do. I'm going to tell you a little bit about the NITRD organization, a little bit about our big data research initiative, mention a couple of the important open and public access initiatives that are going down, end up with one example of something that's happened which seems to me to be a potential best practice within the Washington environment. Some say NITRD, some say NITRD. In any event, we've been around for 22 years, reporting to the White House Office of Science and Technology Policy. There's an eye chart for you that shows the 20 agencies that are members. We'll call NIST and NOAA agencies, even though they're bureaus within the Department of Commerce. So we have pretty much a rogues gallery of federal agencies who support this activity. Within our formal budget crosscut, this represents about $4 billion a year of IT research investments. We have a bunch of sub-areas that we work in: security, high-confidence systems, high-end computing, large-scale networking, software. We recently have a new class of getting together called senior steering groups: big data, cyber physical systems, more security, health, wireless spectrum. So we cover a large number of areas within the IT research and development area where agency folks get together, usually on the average once a month, to plan and do what have you. Big data, I guess you know enough about that. from conferences like this, volume, velocity, variety. I guess there's up to about 7 V's now, and I suppose that's still counting. And we have had a big data initiative in the federal government for the last almost year and a half now. We have 4 initial thrusts: research in core technologies, domain research data, in particular, what can we do when interagency processes would be appropriate. This administration likes competitions and challenges to engage a broader public in thinking about these matters, and we're concerned about workforce development in terms of how we're going to produce the data scientists or whomever we need as we move into this area. In core technologies, number of, I guess I would say, the usual things was done, and last year a joint solicitation from NIH and NSF received a large number of proposals. They're working on a follow-on solicitation. The domain research area, of course, the NSF projects, such have been mentioned, Earth observing systems, astronomy, all of the normal things that you all know much more about than I, plus this thing called data.gov, which is attempting to make U.S. federal data available, are all ongoing. I've already mentioned challenges to engage a broader public, workforce development, how do we do formal and informal education. The 2 important things that happened just within the last couple months that you probably are already aware of: open access to U.S. government data becomes the default. So now an agency will have to argue why some data set that it is holding shouldn't be made public, rather than argue that why it should be made public. And also of great importance to us, the public access to federally funded science articles and data are now required by all agencies funding more than $100 million per year. In fact, agencies have to submit their plans to OSTP by, I believe it's August 22nd of this year, how they intend to pursue those 2 activities. I know how fast the federal government does not move, so I assure you this type of Rome will not be built in a day. Hopefully persistence will eventually win out, and at least raw data will be made available, such as the likes of you, to figure out how to process better and make some increased value out of it. That's my goal, is that we at least get the agencies and the investigators to put the data out, and then worry about the sophisticated ways of processing it thereafter. We're worried about simple things like, where do you put this data? How do you find it? How do you use it? And I expect we'll have rather simplistic answers to many of those questions for the first go-around. One area that's been underway in the federal government for some while, like National Library of Medicine, I think is a good example of what is pointing the way to a semantic future. It's an example of automatic extraction and integration of biomedical information. For 20 years, you probably know the Medline project has been accumulating titles and abstracts of all biomed research articles, and UMLS, Unified Medical Language System, has been creating a glorified thesaurus, or a group of thesauri, which will attempt to categorize concepts and what have you in that sprawling domain. Medline currently has about 20 million articles. UMLS, as I say, is a collection of vocabularies. Based on these 2 long-going efforts, Semantic Medline has been a project also for some time under development at NLM. It's a knowledge base, we might call it, about 3 million key sentences from the 60 million articles, average of 3 key sentences. This is a simplified language, in case there's anybody here who doesn't know what an RDF triple is. The key sentences are derived from the Medline titles and abstracts by linguistic analysis, a fairly sophisticated kind, I believe, and are normalized by a controlled vocabulary derived from UMLS. I've seen it work, and it certainly impresses an amateur like me. Provides a fine graphic view of a specified portion of the semantic Medline graph. As you know, the subjects and objects label the graph nodes, and the verbs label the arcs. Graphic View supports browsing and recall of articles containing the graph links. A Sparkle capability allows for a fairly sophisticated search, semantic search of the information. The goal basically is to connect factoids of information. You've got 20 million disjoint articles. It seems to me that systems like this are in the early stages of presenting a new mode of scientific discovery. Several problems that they've already made contributions on. I mean, the linguist who developed this is able to send in articles to the prestigious Sleep Journal and answer questions that have plagued sleep researchers for sometimes. Why do older men have more sleep problems? Well, he actually connected the factoid here and the factoid here that were too far apart in the literature and submitted the article, and it's published. Similarly, novel connections between cancer, obesity, and circadian rhythms have been discovered by himself, who he claims to be a non-specialist. Well, I raise the question, who will use a new mode of discovery like this? The people at NIH, and he shows it to, take the news very calmly. Seems to me like this is a generational change sort of things, and I expect that it'll be the postdocs and other young folks who say, oh, I can do things here that haven't been done before, and will bring this into existence over time. Some colleagues in Europe have popularized the phrase nano-publications, and their goal is to actually train investigators to write the RDF triples directly, rather than having a linguistic analysis after the fact pick it out. In that sense, semantic midline maybe addresses the past, and nano-publications might address the future, assuming that the investigators are educable, or care to take the time to be educable, which is problematic in my eye. In any event, a combination of these two ideas, nano-publication authors might have a greatly lowered burden of effort by a concurrent semantic midline processing that would enable a dialogue with the authors as they were producing their abstracts, let's say. In any event, this seems to me to be a wonderful possibility. Maybe it's with articles, maybe it's with whatever comes after articles, but if I would like to wake up some morning and find that all scientific disciplines have developed UMLS-like vocabularies, all scientific disciplines have developed semantic midline-like knowledge bases, and all of these various knowledge bases are sufficiently interoperable to facilitate interdisciplinary construction as opposed to construction or as opposed to discovery within 1 square foot of intellectual territory. Thank you very much.
So now let's open for questions, hopefully questions that generate discussion. Maybe you'd like to start off? I'm happy to. Yes.
Oh, I can start off.
No, I'd much rather not me.
Well, sort of touching on this last presentation about the education of computational scientists. So I'm a computational scientist. I'm a chemist by training, but I've educated myself in computational science. It seems like for a lot of the presentations that we have been given, right, that for them to succeed, you have to get buy-in from the scientists themselves, but they also have to have a certain base knowledge level in order to efficiently use the tools. And so would the panelists like to comment on maybe what is lacking in education of scientists in computational science right now, or perspectives on that? I know it's a broad topic.
I'll just share my prejudice.
Okay.
Right, is that I've worked I'm not a physical scientist, but I've worked with physical scientists for 30 years. And there is something that physical scientists get, like I've worked in experiments, right? And the people that succeed in the field understand every data channel, every fact has got to be debugged. And I don't think we drill that into computer scientists. You know, they're more like, if we can connect, we'll give you the things to connect the pipes. And so I don't know that they ever get the kind of experience of that kind of 99% perspiration and 1% inspiration that a physical scientist gets.
Yeah, I can validate that. I can validate that from my perspective, Don, is that upstream, like the joke at JPL is that we hire computer scientists like a master's or even a PhD graduate or whatever, and it's 5 years before they're useful at JPL. Yeah, you know what I mean? Because it takes them 5 years to, learn hyperspectral remote sensing or, climate modeling or astrophysics or whatever, or even to understand at any level, what to do. And like a lot of it has to do with like programming language, like differences and varieties in like, technology understanding, community, like what people are used to and not having that connection, to a lot of these software or these data, communities and things like that. So yeah, I mean, but then the big question, and I don't know the answer to it, is like what's better? Do you take computer scientists and should they be given interdisciplinary training like upstream, like at the graduate level or whatever? Like should they be should half of their should be one of these multidisciplinary data science type of or informatics programs, or do you take like like me, I've had a lot of recent success at JPL with like 4 postdocs, variety of different things. They've been trained from like climate modeling to like radiative transfer models, and then just shoving Python down their throats, or and
works for me too.
Yeah, it's like so which one is better? I mean, I don't know.
Well, as a former academic computer scientist, I would make the observation that there really are 2 disciplines: computer science and computational science. Maybe we're adding a third one now, data science. And computer scientists certainly aren't, well, at least in my department, we didn't well prepare people to go out and work in a scientific computational science environment. I can really believe the 5-year term that you mentioned. We have all sorts of departments of computer science. I don't think we have that many departments of computational science. One thing, it looks like an interdepartmental thing rather than a departmental thing. I know of one university that attempted to put together an interdepartmental graduate program in computational science and didn't even invite the computer science department to participate.
On purpose.
You think you need a new name for computational science to not confuse.
Well, and we did a National Academy study a few years ago on supercomputing, hearing from the computational and the scientists themselves about what are the issues in their field, and they complained bitterly about poor career paths for their supporting computational scientists.
Yeah.
Which seemed to be a significant problem. I suspect we're reintroducing all these problems in data-intensive science that we've had in compute-intensive science. So we've doubled the problems.
Yeah, I mean, high-energy physics is a place where the people that can do things are valued way more than, say, astronomy, and I think exponentially it goes down.
In the projects we work with, the most successful ones are where there's a strong collaboration between the domain scientist who knows what's happening, what they want to achieve, and then the data scientist who's trying to provide the infrastructure to support that. Without that close collaboration, either side could go the wrong way.
Sure.
Yeah, I was just listening to all of you. I was just thinking that you will never, I think, be able to completely separate the computer science portion or computation or data science portion and the people who have the domain knowledge, the astrophysicists, the medical, because you can find all sorts of patterns, many of which will be meaningless, and you need somebody who actually knows the field, the science.
Yeah, but computer science is a science too, right? So there is a large group of computer scientists who are not really interested in multidisciplinary research or collaboration. They focus on their own, narrow, but still scientific problems, right? And I think there is in general, and maybe you can compare Europe to the States also, but in general, I think this culture of multidisciplinary research is changing. Is kind of, I think we are a little bit behind in terms of, there is a need, there is a gap for sure between computer science and domain scientists. And I think we need effort and culture change to really make us work together more closely. Definitely.
I wonder if computer science should do what mathematics did years ago and have pure mathematics and applied mathematics. Some people tell me, oh no, because then they'll hate each other. Just like
They do already.
Yeah, just reinforcing the discussion. It's very close to home for me because literally I run a research centre, which is, if you like, the computational science piece in the same building as computer science, separate departments, separated by a few meters. And yeah, you're right about all the things you just said. it's interesting if you take another example, which is statistics. It seems to be okay to put a statistician on a proposal in any discipline, or for any proposal to train up someone to do some statistics. You don't have the same culture around computer science. I don't know how we get to that point.
Yes. In medical data, especially for cancer research, but not only, for instance, for the common disease, it's very common that doctors, medical scientists look for statistics method to look for some correlation. But it very often happens that the statistics it's not enough because it shows just the relation between two factors. The more advanced methods are artificial intelligence or decision support systems, and they can identify several factors which combined together influence particular criteria at the higher top position. So it shows that the interdisciplinary research is very important, but also understanding that not only simple method is what scientists and many scientists need to solve their problems, but also the advancement of computer science can help them to tackle bigger problems or bigger challenges in the future. And that's the reason for combining those two domains together in the common research.
I want to go back to the reward system for that. I think the gentleman from NTR mentioned that before, and that's something that's like really important. Like I see that. So like I had a paper in Nature that came out in January, and one of the big things that I think I pointed out in that paper from experience is that, you know, we get postdoc at JPL. I have one right now. I'm on the committee for an atmospheric scientist. She's clearly a data scientist. She's studying computer science machine learning graph theories as applied to mesoscale convective complexes to detect them in whatever. But she's using computer science graph algorithms. She's like looking at spark, shark, mesos, GraphX, you know, all these, you know, computer sciencey things that none of her normal committee understand what the hell they are. You know, and so there's a big argument going on at JPL because they want to grab her. But where does she sit? Does she sit in 32, the science division, or 39, right? The computer, and they're arguing, right? But personally, for her, you know, money-wise, it makes sense more for her to be in 39. There's more visibility in 32. Not just at JPL, we see this at, you know, in the university, right? You know, merit-based review, right? If you're, you know, the worst thing you can do is to be more, you know, to be 50% across 2 departments, you know, or whatever, because no one owns it, right?
I think exactly this point was made during the keynote.
Yeah, you know,
earlier today.
It's so how do we deal with meritocracy, you know, for that? How do we incentivize things? I mean, like for me, I don't know, I'll wonk my open source thing, you know, like at least there's reciprocation, you know, in that, like working on cool projects, doing things that matter or that people care about, I think is something that we have to incentivize.
There is no reward for contributing to open source.
I don't agree with that.
Is that a line on your CV which you can use
Yeah.
to get a raise or a promotion?
Yeah, you know, and beyond monetary awards, like MIT, Harvard Business School did a really cool study. In fact, one of the links on my presentation, check it out. It's an RSA Animate video, and it basically shows how money isn't the only reward anymore, right? You know, how basically they did a study and they put bags of money in front of people, you know, and they did, you know, basically they studied the...
So I'd like to remind everybody, our goal here is to define something about data and software preservation. I think as fun as this is, it's getting somewhat off track.
Okay.
So to bring that back, did you have a...
No, go ahead.
Go ahead.
You go.
All right. So actually, I was curious about both Regan and Don listening to your talks. Don, maybe the Dark Energy Survey is a 5-year-long project. So 10 years out, what pieces of the system you're working on now will still have to exist? Like, let's pretend no follow-on experiment, for whatever reason, is not funding.
So have to in the sense that there will be earmarked funding and somebody wanted to pay for it. Nothing, right? I mean, the data will be transferred to NOAO. It will be the top level data that you would, you know, if you began to question it, all you could do is ask who else has studied this data and found systematic defects in it.
Not the raw data, not the actual.
No, the raw data will be there, but all the machinery to process it. Yeah, and there's years and years and years of acumen into this processing that would be gone. So we have right now. So I wrote the last slide to be provocative. I believe no one has obligated me to preserve the software. No one has obligated me to preserve the operational
records. The data is kind of useless, isn't it?
No. I mean, we use calibration catalogs right now, but I don't think anybody knows how they were made.
and they weren't rigorously preserved because some of them were produced 10 years ago, and this was all off the radar.
So that was going to be my follow-on question, which is what artifacts that are 10 years old are currently relevant to the work that you're doing now?
So the work that the stuff that we use right now, we get calibration standards from the Sloan survey, and we get calibration standards from a catalog called UCAT2, if I remember right. And we have never asked a question about it. We know that their data are noisy. We know that there are outliers, and you do fitty, inconsistent things. That's where we get our photometry and our astrometry. So we actually do that, and these things do have utility. And I'm still in the frame of a library conference where I think a librarian is an inexpert person who helps inexpert people find things. Right, that operates at that level, like connect people. We're talking about scientists now. That somebody might want to drill down and find out have a question about the systematics and what's there. And there's only two things to do. You can go examine the production processes. No one's going to build you another $100 million survey, or you can gather the documentation and information that everybody else who has tried to find this, the body of knowledge about that data set, which might be almost just as useful. It might be an easier target to get.
It sounds like, in contrast to the previous keynote, with apologies, it sounds like you're talking there's more value in that documentation coming out than it is the technical.
No, I'm fascinated by the keynote and actually want to learn about. So we just have an untutored approach right now of trying to do good things to preserve our methods and software, right? And I'm unaware of any structure I could plug into, and I'm very, very interested in the keynote, as a matter of fact, because I feel I could learn a lot.
So that actually, sorry, did you want
to? Go ahead.
So that actually brings me, you're talking about a structure to follow on. Watching your talk, you have a huge amount of infrastructure in this IRODS software. Sorry, this is an area I'm not very familiar with, so I have to memorize the acronyms. But in this IRODS software, which is, as you say, a middleware, which seems like it contains many of the pieces that you might want for something like data preservation. On the other hand, looking at it, it's stitching together many heterogeneous systems. It doesn't actually store the data, or perhaps it doesn't really run the workflows itself. It rather transmits its requests down to these other systems. So if you really want to do data preservation, and I'm talking about on the scale of 10 years, 15 years, not on the scale of 1 or 2 years, is that too heavy a system? And is it more efficient to actually extract the data from the heterogeneous systems, store it in a single manageable system, which is all under one agency or PI's control or whatever?
Any system you buy today has a finite lifetime.
Right.
So at some point, you're going to have to migrate from today's technology to the new one, which is cheaper, faster, more easily maintained. So there are many reasons to do the migration. At the point in time when you do the migration, both systems are available. And if you have a system that supports interoperability across heterogeneous environments, you can use it for preservation. So we would like to keep the record unchanged and instead migrate the process that interprets the record to the new technology. So the original bit should never be compromised.
Have you gotten over the migration as an unfunded mandate hurdle?
Yeah, that's
we do it because people want to reduce costs. Running old equipment is expensive. They always go to the cheaper, newer technology whenever possible. And so the answer is we do the migration, we automate the migration so there's no labor involved. The system's doing it for you. But the result is you end up in an environment which is cheaper to run than what you used to have. And therefore, you go to whoever is funding you and tell them we're saving you money.
So Reagan, I think there's a couple kinds of migration going on here. I think you're in a very unique position to answer this. So if we go back to SRV did exactly what you're talking about. You had underlying storage technologies, but you still had a common front end that the user would come to. And now, sort of in generations of technology, you've gone from SRV to IRODS, which is an evolution of that front end. Do you have any stories to tell about people who have migrated across those front ends as well? Do the bits stay the same, or is it a conceptual migration?
So I think of the front end as the client I use to access the data grid.
Okay.
And right now there are more than 50 different clients because everybody has a preferred access mechanism. Whether it's a workflow, a digital library, a web service, a web browser, an IO library like Fortran, a load library, a Unix tool, a grid tool. They're all interfaces on top of the middleware.
Sure.
So that's the challenge of the middleware. It's interfacing from the external world, the client you want to use, to your storage system, which may not understand the type of client you're coming from. And somebody has to do that translation. So when we're doing migration, we're either porting new clients on the system, or writing drivers to talk to new storage systems, or new authentication methods, or new transport mechanisms. We're basically an interoperability mechanism.
But you must have cases of people who have migrated their data sort of through the generations from SRV to IROC. Right?
Yes.
And there, it's not only the files and the bits; it's also the metadata and other stuff. Does that end up being a one-to-one perfect? Perfect is not the right word. Identical replication, or is there some transformation that happens as you go through this technology?
Since the technology is agnostic as to either the format or the meaning of the metadata, I can migrate any set of metadata from the server and make it appear as metadata in IRODS with the same meaning. IRODS doesn't care. So people have migrated petabytes of data between the environments.
So we should probably wrap this up because we've hit we're actually 5 minutes behind on the schedule, and we have another roundtable, which is yours. Start getting into that. So I think what we'll do is take about a 5-minute break and then come back to the next roundtable. That sound
Yeah,
good?
so that'll be the next panel. Doug will moderate with Micah Altman, Matthew Mernick, and Michael Witt. So if you haven't given your presentations to Kelly yet, please do, and we'll kick off in 4 minutes at counting.
Because Michael Altman, who's the Director of Research at MIT Libraries. Go ahead and take it away.
Hi, I'm Micah. I was originally trained as a software engineer and then formally trained as a social scientist and then libraries and preservation rubbed off on me, so I built scholarly plumbing. So we've done a bunch of related work. I won't talk about that directly. But I took the title of this workshop seriously and literal-minded like that, commonalities with other disciplines. So I'm going to talk about social science, and to make sure I understood the DASPOS commonality, I went and read all the reports on the DASPOS database. So it was very so we'll talk about the landscape, and I feel in representing this field that there's just so many different varieties of social science that all I can do is call attention to some of the dimensions of this multidimensional landscape, and then pick out a few landmarks. So what are some characteristics of research data that might be relevant to preservation? Structure, we've got unstructured stuff, we've got semi-structured, and pretty much any sorts of structure you like, attribute types, measurement scales, performance characteristics. I haven't seen multi-petascale. The closest is Facebook, where social scientists are doing analyses of Facebook data. It's not quite top scale. Social scientists might be interested in pretty much anything that has to do with people, institutions built by people, interactions among people, mental processes within people. We sort of veer off at studying pieces of people like fingernails, but units of observation vary widely, as do the measurement types and the quality of the data, the ontologies, metadata, often towards the poorer size of things. We've got a lot of different methods, and I think there's a saying in social science that the crappier your data, the more sophisticated your methods have to be be able to make any sense of them at all. So people are doing a whole lot of different sorts of stuff, and the desired outputs vary. There's also a set of very interesting constraints on social science data. The most common and persnickety constraints are around information privacy and confidentiality. But there's also issues having to do with licenses. Some of this data is commercial, so you've got NDA, intellectual property on database rights, and funders with their pesky open access requirements. So that's a very, very broad landscape. Let's focus on 3 use cases, and we'll make some unsupportable predictions. So one exemplar on the sort of simple side is policy analysis, and not to oversimplify, but I'm taking one of the simplest examples here. So National Science Foundation runs the National Center for Science and Education Statistics. They conduct surveys of individuals with PhDs and institutions and business concerns, enterprises that do research funding to elicit things about how people with PhDs are getting jobs, what they're doing, where research and development spending, and this heavily influences pieces of policy. So this is used by public administration types, by congressional staff, by the National Science Board, and the pipeline's pretty simple. There are a bunch of people and institutions. There's an instrument. It's observational data that you're going to elicit it. It goes through actual NCSES, which is actually a web of subcontractors. And if you want to know more about this, we did a National Academy of Sciences set of recommendations on how they can improve their policies.
And they produce tables which then are used for simple graphs, all based on counts, contingency tables. And that drives these policy reports. And that's the evidence. That's on the, that's a landmark on the simple side. And simple data, high quality, lots of metadata, not perfect in any way perfect because you've got these messy human sensors. But that's on the high effort, high quality data side of the scale. Here's another example, sort of on the other side, on the resources involved. I was at Harvard for 15 years. One interesting thing there is the Department of Anthropology has a PhD in media anthropology. And each of the students in this PhD program goes out somewhere. They collect lots of observational data. They interact with people. So there's interaction here. They're not necessarily a formal experimental design. They take their recording instruments. They get hundreds of hours of video, and then they code it. Field notes. Sometimes they pay transcribers to transcribe it, but they code more than the things that were said. They add their field notes, they code those to create quantitative data, and then they produce both a dissertation book and a 2-hour media project that is part of the intellectual work that is evaluated for their dissertation. Unfortunately, what happens is that is stored on a DVD-ROM that's talked into the back of the dissertation. But the thousands of hours of data that goes, or hundreds of hours of data that goes into all that observation is probably kept on their laptop until they get a new laptop. Here's another landmark. Some colleagues at Northwestern, MIT, Harvard, social message analysis. These are microblogs. So the idea is that the data producing mechanism are the crowd of people plus some events in the world creating these signals, which are texts, these people talking to each other. This is mediated through Twitter and Weibo and other services that collect all this stuff. And then my colleagues in various places, higher institutes of learning, write bespoke code and run it in the cloud and grab all of this stuff and start saying, oh, when does China start to suppress, how does it apply censorship dynamics? Okay. What are the relationships among, how does this information propagate out? And so this is data structure that includes both the text, the codings of the texts, and a network of relationship, all of which changes over time. So, what are the trends here? To more, as in other fields, more data, more open, more learners on this data, more publications and filtering. Most recently, I'm starting to see more replication. One of the projects I'm involved in is building an integration between an open journal system and a data repository system, OJS and DBM, so that when somebody submits an article with supporting replication data, that can be managed continuously, part of the review process, and then put in an archive that treats it more than as a blob of bits. But there are journals, replication policies from the journal side, from the data side, from the code side, and even from the sort of policy side, where you register the fact that you're going to do a replication first. You get the design published, and that gives you an incentive to actually do it. So what are some of the challenges? We've got noisy human sensors, mixes of data types, complex constraints, manual and computer-assisted coding. The coding of this from raw data through coded data can't be captured entirely by any particular closed-form scripts. Niche commercial software is often integral to analysis, as as is bespoke software, because sometimes the algorithms used are defined by the software. That's often true of clustering. And a lot of these have very long-term longitudinal data accessibility requirements. NCS, long longitudinal data sets may be required to be accessible and be, in some extent, replicable over 50, 60, 70 years. So that's social science. Thanks.
Thank you. Our next speaker is Matthew Lear.
Great, thank you. So I now have the challenge to try to talk about the geosciences in the same sort of 10-minute period. And I'm going to kind of, instead of doing what Michael did, sort of punt a little bit and do some very coarse general. Data. So here's my characterization of the geosciences, and basically the point here is that it's very difficult to characterize the geosciences in any short period of time. So what I'm going to do is give this very general picture and then go specific, like I said, to NCAR. So big picture is there's some very robust, high-quality collections, and the acronyms, I'm not going to spell them out, but basically the government agencies of various kinds. Some of them I'm sure you recognize. But I say some very robust. So there's also a lot of research done at universities and other centers that are not that do not generate data that end up in sort of these high visibility collections. Similarly, there's some very well-established and widely used standards, but again, some standards, and there's a lot of data that's collected in ASCII, sort of general purpose data formats that are not do not follow standards. This goes both for data and metadata. So I think that in lieu of going any sort of farther sort of generalized here, I'm going to get into NCAR, because NCAR has a lot of the same issues. We have some very robust data collections, and we have some data collections that are not robust and sort of preserved in the sense that we're talking about here. And again, some groups use standards to a very high level of efficiency, and some don't use standards at all. So this is the sort of broad scope of what NCAR does. It's a research center, National Center for Atmospheric Research, funded by the National Science Foundation. UCAR is the management entity of NCAR, so you can sort of think of them as the same, two parts of the same organization. UCAR also has some community programs, which I'll describe in a second. So you may not be able to read the words, but basically everything you see in this slide is kind of research that's done at NCAR. We typically, although it's called atmospheric science, we typically think of it as Earth system science is what we're really supporting at NCAR. So it's how to characterize solar aspects of solar inputs to our Earth system, ocean inputs, ice inputs, and of course the atmospheric circulation that and ocean circulation that moderates a lot of these behaviors globally. And so NCAR provides, NCAR both supports science that's done internally, so we have around 500 scientists who do science based at NCAR, and we also provide facilities that enable the university community to do research using capabilities that any one university couldn't support. So for example, we have a supercomputing facility that was opened up recently at Wyoming, Cheyenne, Wyoming, called the NCAR Wyoming Supercomputer Facility. And this is the latest in a history of supercomputing that NCAR has supported over the years. Another kind of facility or sets of facilities are data facilities, and this is just a website that is linked from the UCAR page, but lists a range of data services that UCAR provides. And these range from data collections that we bring in from the outside. So we have a research data archive that brings in data sets from NOAA, NASA, USGS, as well as other sort of research-based data sets to make it easier for our scientists and community scientists to access all of these in one place. We also have large collections of field project data that our own scientists have produced, climate simulation data sets from the large climate models. UCAR also provides data tool development, so there are infrastructure development teams at NCAR developed things like the Earth System Grid, which is a climate model data sharing facility or service. It's international in scale. And Unit Data is a UCAR program that has developed many different pipeline tools to bring in weather service data from the Weather Service to universities, as well as the NetCDF standard that was shown on my first slide, which was developed at Unidata, and it now is becoming a community standard. So what I'm going to talk about for the rest of my talk is some strategic initiatives that we're working on right now. We have a strategic planning process going on, an IT strategic planning process, and data services is one component of that. And so I thought it'd be interesting and I think relevant for this group to look at these strategic plans to think about preservation as one piece of this. So preservation is one of our plans, but it's only one piece. So in general, what we're trying to do with these strategic plans is develop what can we do for our organization that starts from where we are and sort of gets us to some place that's in 5 years more robust and continues to be a leader in this area. So the education component was discussed earlier. The scientists who are creating data, if they don't understand preservation, it's going to be much harder for us to provide services that help them preserve their data. So education is just the first piece. Guidelines for helping scientists as well as the data management teams around the organization understand these sort of best practices and principles. And one of the goals here is to develop what those best practices might be. So it's maybe not develop them ourselves, bring them on the outside where they've been identified. Archiving and access. And so we have, as I mentioned, some robust data collections, but there's a lot of the sort of orphan data issue that you have in any other organization or any other domain. So we're looking at what is the best way to do this. We have some systems in place that could be potentially adapted to be a sort of orphan data collecting system. But there might be others out there that are already in place at other locations that we can sort of pull in. So this issue of orphan data and small-scale data sets that are housed in many different locations around the organization is a big one for us. And the sort of what's indicated in black here is some of these are longer-term initiatives and some are near-term. But in the shorter term for this one, we should be able to identify what is sort of best types of options for doing orphan data collection in other organizations. Discovery is another one. So I showed you that website earlier that has the list of data archives, and really that's the only place that even brings those data sets together. There's no sort of central discovery mechanism around the organization for our data sets. And this has been, over the past 20 years, a number of initiatives that have tried to address this in one way or another. So the community data portal was one of those, and this was a development of a portal, as the name suggests, for NCAR data. So it's kind of pulling metadata from a lot of different groups to try to provide a central discovery. But this is kind of now an old effort. It hasn't been updated in quite a while. And it's not taking advantage of the sort of network architectures that we are interested in now, where discovery is done at sort of multiple locations. If you're using the portal approach, if people don't know that your portal exists, it's not really getting you very far. So looking at sort of ways to do more sort of distributed discovery, whether it's sort of another layer, as was discussed earlier, around providing a uniform discovery layer, or something like sort of more network discovery. And there's a couple tools, GeoPortal and OpenSearch, which we're looking at as kind of potential pilot cases. The preservation, as I mentioned, is one piece of this, and as was discussed earlier, that this is more than just the bit-level storage and bit-level preservation. It's also about having some sort of basis of understanding what you have in some period of time and regularly at this point. So it's not just collecting the files, it's collecting metadata that describes the files. It's collecting perhaps software and code that were associated with that. We've done a short survey that indicated about 75% of the scientists around NCAR use original scripting when doing their data analysis. So collecting the code that goes along with the data is something that's very critical. So external integration is another one that I think is important to think about. And the point here is thinking about not just who are the data users now, but who are the data users going to be in 5 or 10 years, and what will they be interested in doing with your system. And so there's a lot of discovery and data archiving systems being built right now. And the point here is that are we just building another sort of network, or not network, but set of silos that we're going to be trying to network in 5 or 10 years? The example that I mentioned earlier, the Earth System Grid, was one really sort of high-profile effort in this area in the past decade, where this was a climate model and climate model results and climate model simulation data sharing system, which was developed to specifically address the issues that came out of sharing model results from previous climate model intercomparison projects, which are sort of international projects to compare how climate models do the same type of experiment. So 20 different universities or organizations run similar experiments with different models. Do they all show that, for example, the climate will get warmer, or the precipitation will increase over the next 20 years, given their different model structures? So that's one initiative. APIs, I think we all know about those, so I won't go through those, but that's something that needs to be done. And so my basic sort of conclusion here is that this is a largely human effort. We need to have technology, but we need to have sort of the human support to do that. We may not be able to do all of this, so we need to have some sort of organizational structure to decide what the priorities are. I think this is not just an NCAR thing. A lot of these really cross over with multiple organizations, so I think I will stop there.
Our third speaker is director of the Purdue University Research Repository. Did I get that right? Yep. Michael Witt, is your slideshow there?
Yeah, thanks. We got a lot of things
Yeah,
here.
Yeah, it's right there.
All right, thank you very much. At Purdue Libraries, we're interested in practical solutions for data curation. Being able to answer the question that George asked earlier, where can researchers put this data? And so what we've done is the libraries have collaborated with our research office and sponsored program services, as well as our campus IT and research computing departments, to put together a university research data repository that's based on the Hub Zero open source software. It's a scientific collaboration platform. David mentioned it earlier in the day in his keynote. And so this is just one repository that fits into an ecosystem of other kinds of data repositories. And this is not a complete list. It's not any kind of typography. The point I'm just trying to make is just that there are different groups of activities around research data curation. Some of them revolve around publishing activity, such as journals in evolutionary biology and the Dryad repository, which just announced this morning that they're working with Elsevier to link reciprocally between data sets in Dryad and the published scientific literature. Disciplinary and subdisciplinary repositories, consortial repositories, like ICPSR at Michigan. You have countries that have federal initiatives, like in Australia. You have government agencies or government data repositories. You have research centers. You have instruments that were talked about earlier that generate tremendous amounts of data that have repositories associated with them. You have these kind of general purpose internet data repositories, things like IBM's Many Eyes or Figshare. Over at Micah's institution, you get things like Dataverse, where you can roll your own repository. And then the thing that I'd like to talk about a little bit today is just one piece of this ecosystem, an institution trying to provide a core facility for data deposit on its campus. And so you go to these data talks and talk about the value of depositing data and sharing data and reuse and advancing knowledge. And you always end up with some kind of life cycle diagram, something like this. And so my personal metaphor, though, is the Lion King, the circle of life. What I want to do is I want to show you, present our repository to you in the same way that we present our repository to our campus community, which is through a 4-minute YouTube advertisement. So if you can tolerate a commercial, I'll play this for you so you can be introduced to the repository in the same way our researchers are. But I want you to keep in mind that we're not really trying to provide just a simple data publication platform. We're trying to support the entire research data lifecycle. So getting involved early and upstream in the research process, and from a library's perspective, looking how we extend library services. So things like data management planning, organization, description of data while the data are being generated, so that it's suitable for later deposit, curation, access, and reuse. So with that, I'm going to attempt to
Welcome to the Purdue University Research Repository, or PUR. You can access PUR on the web at purr.purdue.edu. PUR is a web-based platform that researchers can use to share data and collaborate on research online. In this video, we're going to give you a brief overview of the 4 main ways that you can use PUR. You can use PUR to create a data management plan for a grant proposal, to collaborate with other researchers, to publish data sets, and archive your data sets in a secure, trustworthy digital repository. If you submit a grant proposal to the National Science Foundation, you'll be required to write and include a 2-page data management plan with your proposal. Many other research funders in the U.S. are beginning to require data management plans, such as the Department of Energy, NEH, EPA, DoD, NOAA, NIH, and the USDA. PUR can help you get started to write an effective data management plan by providing example plans, tutorials, videos, and other useful resources. If you'd like to use PUR to manage your research data, we provide boilerplate text that you can copy, paste, and edit in your grant proposal. Any Purdue faculty member, staff, or graduate student can create a project on PUR and receive a default allocation of data storage without any cost to them. They can register a grant award with the project and receive a substantial increase in their allocation of storage, also at no cost to them. After creating your project, you can invite collaborators from Purdue or other institutions. Your invited collaborators will receive an email with a link for them to click and access your project. PUR was built using the HubZero platform for scientific collaboration, which includes a powerful set of tools for sharing data and facilitating online research and collaboration. For example, members of a project can upload and share data files with version control and social network-style communication and project management features. Access to the project space is limited to the members of the project. If you're ready to share your data with the world, you can publish datasets from within your private project space. Simply select the files that make up your dataset, provide some information about the dataset, and submit it for publication. Published datasets are presented with rich metadata, making it easy for people to find and understand your research. Purdue is one of only 3 data site agencies in the United States who can issue digital object identifiers, or DOIs, for datasets. A DOI is a globally unique and resolvable identifier for your dataset that makes it easy for people to cite your data and give you credit when they reuse it. PUR emails users a report every month to show them how many times their datasets have been accessed. Many researchers find that publishing their datasets increases the number of citations to their published work and improves the impact of their research. Your published datasets will be securely and reliably preserved in PUR for a minimum of 10 years, after which time they will be supported and managed as a part of the university's library collections. PUR was designed and is maintained with the current best practices and standards in digital preservation. We're currently preparing to be audited as an ISO 16363 trustworthy digital repository. In summary, Purdue researchers and their collaborators are taking advantage of PUR to write data management plans, collaborate on their research online, publish their data sets with DOIs, and archive their data in a secure, reliable repository. Since its launch, PUR has been included in the data management plans of over 700 grant proposals. If you have questions about PUR or research data management services, please visit the PUR website at purr.purdue.edu or contact us by email or telephone. PUR is a university research core facility that has been made possible by a collaboration of the Office of the Vice President for Research, Information Technology at Purdue, and the Purdue University Libraries.
So thank you for suffering through that. That seems safer than trying to do a demo in the space of 10 minutes. So that's how we present PUR to our campus community. We're trying to speak to a different audience than obviously we have here in this workshop today. Just to talk a little bit about how we brought this together, the people who were involved, how it's governed. We have an executive committee which consists of the Dean of Libraries, the CIO, and our Vice President for Research. So they make high-level policy decisions and resource allocation. We have a steering committee that includes representation from the libraries, from the research office and sponsored programs, and from research computing, as well as 3 domain researchers from our faculties to represent user interests. And then the project personnel, myself as project director, I'm half-time. We have technologists, so web developers, software developers, middleware experts, security expert. We have a hub liaison, a metadata specialist in libraries, a digital archivist, and then a digital data repository specialist who's the primary point of contact for PUR. So about 6 FTE to launch this in the first 18 months at an expense of about $833,000, just to give you a point of reference. So we've just done an assessment of PUR, and we've applied for the next year's worth of funding. Within the next year, we hope to achieve steady state, which will probably be roughly half the FTE. So, has this been effective? So over the first 18 months while we've ramped up the service, we've been monitoring data management plans that have been submitted by our researchers to funding agencies. SPS will give us a report every month. We have about 720 DMPs that have mentioned PUR as a primary component of their data management plan, 49 grants that have been awarded. We've signed up almost 800 researchers from Purdue. We've created about over 200 research projects. And then in the last month, I sat down and we coded the most recent NSF proposals that came from Purdue to see what our researchers citing in their DMPs. About half of them were using PUR. Another about 30% were using their local eLab notebook, their department server, some other local solution. 14% were using some disciplinary repository, things like ICPSR, the Protein Data Bank, NEAS or NanoHub, and 8% of the proposals were for funding that wasn't producing research at all, or wasn't producing data, I'm sorry. So to talk just very briefly about, yeah, is this being recorded?
Yeah, actually.
So those 8% are producing valuable research, just not producing data. To talk very briefly about preservation and design, you heard in the video we commit to 10 years of stewarding the data. As we approach the end of that 10 years, the researcher or his or her department has the option to pay to continue to maintain the data. After the end of that initial commitment, if they don't pay, the libraries then takes over the collection. And we support it using our collection development policies, just like we apply them to other kinds of traditional library collections will be applied to data sets. Our design has been guided by the Trustworthy Repository Audit Checklist, or TRAC, which hasn't been mentioned in this workshop yet, but is a very valuable document, and has become the ISO 16363 Trustworthy Digital Repository standard. It has these 3 sections. It's a very comprehensive way of looking at digital preservation systems, not just from a technology standpoint, but in terms of your organization, governance, business plan, policy, digital object management. And of course, we did a risk assessment of PUR about 1 year into the project, which was a terrifying but very enlightening process that we're going to repeat here within
the next year to see how we're doing. Any preservation system should talk about their archival information package. As was mentioned earlier today, technologies crumble and fall into the sea, and so you want to know, what color is your parachute? That's your AIP. An AIP in PER uses the Library of Congress BAGIT specification. Essentially, there's a bag declaration file, a manifest file, which includes a location of all the data files, as well as fixity information, plus the data files themselves. One of those data files is a serialization of all of our metadata. It's essentially a METS wrapper that includes descriptive metadata, Dublin core, and mods, along with our preservation metadata, which is in premise. And then we're in the process now of integrating with the Meta Archive, which is a private LOCKSS network, which replicates content to partner institutions, 7 copies. So it's $1 per gig per year, just for point of reference. So we've been doing this in a fairly generic way to support data research collaboration and data sharing and data publication and digital data preservation. We want to move into having the same types of services for software. So instead of visiting the web page and uploading data files, we want to be able to integrate with things like Git so that you can go ahead and just check your files in directly if you're writing code. We want to enable the online development and publication of software tools. The best example of this currently is actually another hub called NanoHub. So if you want to see an example of executable simulation tools online, you can go to nanohub.org, and you can see where we want to go with PER in the next year. And I'm out of time, so thank you for your attention.
Okay, so we have some time for discussion. I have a whole pile of questions. There's got to be some. We heard from research libraries. We heard from NCAR. We heard from MIT. Is that a question? Yeah, question. Go.
To Mike. Mike, so the workflow that you described, who provides the metadata? Is it the researcher himself herself, or it's the librarian?
So a good question. I didn't have time to delve into that in the 10 minutes. So we've tried to extend our library service model using PER to data. And so what happens is when a researcher creates a project in the system, the appropriate subject specialist liaison gets an email message letting him or her know that a project has been created based on the department affiliation of the researcher. So if it's a civil engineering faculty member, our civil engineering librarian gets an email saying, hey, Dr. Jones created a project. It's an opportunity, it's not an obligation for the librarian to consult and to be able to influence the process. The next point of integration is if a grant is awarded. When a grant is awarded, then another more strongly worded email goes to a librarian saying, you really need to consult with Dr. Jones because he has committed to using PER, and so that's more of an obligation. The next point is when a data set is submitted for publication, it's not immediately published. What happens is it sits in a queue for up to 2 business days where a librarian, again a subject specialist, has the opportunity to review it. They're not peer reviewing the data, they're just looking to see that it's an appropriate use of the system and that it has a full description and that kind of thing. And they can have a discussion about improving the description. In some cases, the librarian may step in and just do it, or the metadata specialist may just do it with the consent of the PI. And then at the end of the initial commitment, so 10 years or longer down the road, when the data sets are remanded to the libraries, it's the subject specialist librarian consulting with the digital archivist to make a selection decision about whether to keep the data set or not. And so 10 years is kind of arbitrary, but a lot of these preservation systems that you see, they end in like ... question mark, Like at some point in the future, somebody is going to do something. Otherwise, the assumption is we're just going to keep everything forever. And that's not a realistic assumption. And so what we've said is 10 years, we'll budget for that, and we'll use that as a target, and we'll put some procedures and policies in place to be able to make decisions. The default policy is deaccession of data. So if nobody does anything, the data go away, and they're replaced by a deaccession notice, which is a skeletal metadata description of the fact that the data existed. So the DOI, we've committed to resolving the DOI
it will resolve to the exception notice.
How many university libraries are providing services like PER? Do you have any idea?
There are a handful in the United States, but this is fairly early days. There are a lot of different approaches. So many of the approaches are more project oriented than generic services. So ours is a multidisciplinary repository that we're trying to support the data needs across the university's support facility.
It's like a good job for 21st century librarians.
Yes, and we're hiring incidentally.
There are additional technologies from the digital library community like DSpace and Fedora. Do you interoperate with those?
Yeah. So interoperate, we provide some interfaces for interoperability, but they're fairly rudimentary. So like we support OAI-PMH for metadata harvest and index. The data site, DOI metadata is indexed and provided, combined and aggregated with a lot of other different sources of metadata, and that's one point of integration.
What scale do you anticipate the system going to? So if somebody came with 100 terabytes and they tried to put it into Hub Zero, would it handle that?
Well, so right now the way this is governed is the video, we didn't actually put numbers, but there are quotas in place. And so the idea is any Purdue faculty member, graduate student, or staff can create a project, and they get a default allocation storage for their project, which is 500 megabytes currently, and they get a default allocation for public data publications, which is 10 megabytes. If they associate a grant award with their project, that goes up to 100 gigabytes and 10 gigabytes at no charge to their grant. We just want to incentivize sponsored research. And then beyond that point, to avoid getting clobbered by like the big data projects, like some that have been discussed here today, we have a storage pricing menu, and people can purchase storage then. We haven't had anybody take us up on it yet, but it's available there.
What's the wholesale price?
You can go to the website and see. If you go to per.purdue.edu and you go to getting started and something like that, storage, it's up there.
Right. But if somebody is seriously coming to you with 100 terabytes or a petabyte of data, is the library prepared to take that on? I mean, how are they going to manage it, and what are they going to do with all that?
Yeah, I mean, it's a good question. Right now, the way the system works, it kind of governs against, the ways that we have to ingest the data are fairly simple right now. These kinds of things, but we want to talk to people in bigger projects because where there's we have resources to be able to build on top of the system to accommodate. We want to be able to do that.
Are you coordinating with like information technology? I think this is kind of a common question in a lot of campuses. As the data gets far, just the library trying to provide the services, the information technology, computing services, the school, and department, something like that.
Right. So it's a collaborative effort. So when I talk about the per team, it's research computing, which is our campus IT, libraries, and the research office working together, represented all levels, from personnel to our steering committee to our executive committee. And so, like for example, as a librarian, I'm not doing storage engineering. We have a storage engineer who works in the Rosen Center for Advanced Computing who takes care of that, which is why I can't address specific questions about storage technology and that kind of thing. But they know about that, and we have those folks on the team. Same thing with the risk analysis. To have someone who's a PhD with the Sirius Center be able to do a comprehensive risk analysis, really, really valuable. This has truly been a collaborative effort. It's not just collaborative, in terms of on paper. We meet, the project team meets on a weekly basis, the steering committee meets on a monthly basis, the executive committee meets on a semesterly basis.
You said the effort profile is going to go down to half an FTE?
Roughly half, not half an FTE, 3 FTE. So probably from 6 FTE down to about 3.
What's your guys' strategy for like hiring, these library experts and the metadata experts? I mean, I could imagine, it's along the lines of questions already been asked, but it's not infeasible to have terabytes of data if I get funded on some grant, but additionally it could be very specific. Like if I got funded on an MSF, major research instrumentation, to go like stand up some towers in the Sierra Nevadas for water or snow and things like that. Like how would you guys would you guys only be responsible for like the archiving aspects, or are you going to populate FGDC metadata for me, or something like some of that? Like at some level, there's a boundary, right?
Yeah. So what we tried to do is because there's so many hypothetical situations, we've tried to iterate and take things as they come. And so we know there are some things that we have to accommodate. Like we know we have to accommodate software source code as one content type. We know we have to accommodate geospatial data better than we do as another type. And so those are the kinds of things that are, we're rolling out basic services now, but I hope that we'll be able to scale out and increase the breadth to be able to do some of those things, like at GDC search.
What's your profile like? Do you have people that are doing those types of projects now, or if most of your metadata that your librarians are capturing the big ISO metadata for the electronic resources, or Dublin 4 or something, like that, or whatever,
Right. So we hired a metadata specialist in April of last year who's focused on digital data description, new kinds of content. And so we have 20% of her time now, and that's not going to be enough moving forward. That's already a bottleneck for us.
So I have a question for, where did Luke? Oh, there. So one thing you brought up in your, I was going back through talking, so two questions about your talk here. Do the second one first here. You mentioned it very briefly in passing, you have these projects that have gone on for 50, 60 years collecting data. And I just skipped right over that. I thought that was very interesting. Could you tell us something about these social science activities that have been collecting data for that amount of time? Was that anthropology?
No, that wasn't anthropology. The National Center for Science and Engineering Statistics, how far back they go, but that's a longitudinal data collection that spans a couple of decades, I believe. The panel studied income dynamics, the General Social Survey, American National Election Studies. These are longer-lived surveys. There are a number of looking at the Murray Archive at Harvard. There are a number of individual researcher. One is that Luke studied human development that was a longitudinal survey of or maybe it's, I forget which one, but Google grant. And that started in the 1930s, and I interviewed with the same panel of people more than 50 years. So a lot of social sciences built on official statistics. You can get census data back for quite a while. And a source of integrated census data, including integrated GIS, the HICOMS project. So those are a number of different data points.
So I think we're almost out of time in the session. Do we have one more party question for a few things?
I'm interested in the approach you're going to take for federation across repositories for NCAR.
So we're still looking at the best way to do that. A couple things I mentioned are GeoPortal, which is sort of a geospatial, essentially sort of a discovery layer based on geospatial data. And so the idea is that the different archives sort of set up GeoPortal as on their own systems, and then they identify each other as sort of cross-cutting collaborators. And then the GeoPortal discovery layer, they connect their metadata databases to that, and they provide sort of the federated search. So from one, you can discover resources in the other.
There's an effort between NASA Langley and NASA Goddard to federate their DACs now. So it'd be very interesting to see if yours could also federate.
Yeah, I think we've had some discussions with NASA. At least one of our archives to try to do that as well. So it's that's good.
Have you thought of doing that beyond your own agencies? I mean,
Well,
ultimately, you know, that's its own still silo.
Yes, definitely. Ultimately, yes. I think the idea is to get ourselves in order, and looking at other things like what was mentioned by Reagan as kind of pilot examples of doing it across organizations. Definitely a longer term goal.
Okay. With that, why don't we take a 5-minute break? I believe our next step is we're splitting into parallel sessions here. We've got the paper presentations and also the DASPOS. Do we have a location for the?
We can immediately convene at the 4 tables set up back here, and then for each group we'll have policy-based data management with Reagan and Elizabeth. If you could stand up, Elizabeth, so people can see you. If you want to join policy-based data management, join Elizabeth's table with Reagan, and you can either continue at your table in low voices so you don't interrupt the paper presentation, or you can reconvene outside but return here around 4:15. Similarly, for reuse of big data, that will be done Petrovic with Micah Altman and Rob Gardner and Yarrick from DASPOS. Rob and Yarrick, if you could stand or make yourselves visible so people will know who to look for if you want to be reused of big data. Software and algorithmic preservation for open science will be Chris Mattman with George Strawn, and you'll be with Doug Thane. Doug, make yourself noisy for a minute. Blue shirt. Join Doug for software and algorithmic preservation, and finally access, query, and linked open data. We'll have a lead off with Lynn Bouchard from Oak Ridge National Lab. She'll be with Chuck Bartman. Chuck, stand up, look for Chuck's table. He'll be your DASPOS PI for that effort. And look for your group at the tables in the back in about 5 minutes, and then you can either remain at your table quietly or find another place outside where you can be noisier. And join us back again at 4:15.
I just wanted to make one minor announcement. There are the photo